Learning-Augmented Robust Algorithmic Recourse is our contribution to algorithmic recourse. Let's first understand what algorithmic recourse is by looking at an example of a woman named Alice who applies for a loan at a bank. The bank uses a black box machine learning model to decide whether to approve or deny the loan. In our case, the model unfortunately denies Alice her loan. So it would be helpful to Alice to not only receive an explanation for this decision, but also to get a counterfactual suggestion showing what she could do to increase her chances of approval next time. Here is an example of a counterfactual recommendation that offers Alice 3 possible changes she could make. She needs to increase her income, decrease her debt, and open a savings account. To put it more formally, algorithmic recourse identifies the minimal modifications a person can make to their feature values that would flip an unfavorable decision into a favorable one. Here we have a classifier that maps inputs to 0 and 1, and we have a cost function c to quantify the cost of modifying x0 to x prime. This is the exact formulation. Another way to express it is by relaxing the strict requirement that the model output must be exactly 0 or 1. Instead, we use a probabilistic classifier that produces outputs between 0 and 1, and this lets us rewrite the original formulation in a relaxed form. The relaxed objective has 2 components, the cost and the validity. We still aim to keep the cost low, and at the same time, we want the model's output f to be as close to 1 as possible. We measure this closeness with a loss function L. Since these 2 objectives might conflict, we introduce a balancing parameter lambda. If lambda is set to a very small value, the optimization will prioritize achieving an output close to 1, even if the cost becomes high. On the other hand, if lambda is larger, we focus more on keeping the cost low, even at the expense of the model's output being further from 1. And ultimately, depending on whether we use the exact or relaxed formulation, the choice of model, and the type of cost function, we end up with different optimization problems. Now I'm going to define the price of recourse as the following term. So we want to find a solution that minimizes this price of recourse. Once Alice receives a recourse recommendation, it might take her several months to act on those suggestions. So for example, it might take Alice 6 months to increase her income. And during that period, the bank's model could be updated. And there are different factors that could make the bank to update their model. For example, the Fed may increase interest rates, which would cause the bank to update their model to reflect this change. Now, while the original model would have approved her loan after she made the recommended changes, there's now a concern. Will the updated model still approve her application? Most likely not, because the recourse advice was tailored to the original model, not the new one. So in this way, model updates can render previous recourse invalid. Now, how can we represent these updates in models? A standard approach is to use the LP norm. For example, if we use the L2 norm, or the Euclidean distance, then in 2 dimensions, every point inside this yellow circle centered around the original model theta corresponds to a valid updated model. The goal of robust recourse is to provide recourse that remain valid even when the model changes in an adversarial manner. In other words, we want to generate recourses with high validity even in the worst case model update. To handle this, we add an inner maximization over theta to our recourse objective as shown in yellow. And we are trying to find a solution that minimizes the price of recourse, while the adversary is trying to find a worst case model that maximizes it. And there have been many methods that tackle this problem. A well-known example is the gradient-based approach called ROAR, which can be applied when both the model and the cost functions are differentiable. But ROAR doesn't always converge to a stable solution, and more importantly, it doesn't guarantee finding the optimal solution. And additionally, the recourse recommendations produced by ROAR often come with a high price. To address these challenges, we designed an optimal algorithm for robust recourse. Our method assumes the model is a general linear model, such as logistic regression. We construct the set of adversarial models using the L-infinity norm and choose the L1 norm as our cost function. The algorithm is an iterative, greedy algorithm where in each step it identifies the best candidate X and then determines the worst-case model corresponding to that X. And this process yields an optimal robust recourse. Moreover, because it's greedy, the algorithm typically changes only a small subset of features, which translates to fewer practical changes that a person would need to make. Although our algorithm is designed for linear models, it can also be extended to work with nonlinear models like a neural network by locally approximating them with linear functions. And for this local approximation, we use Line. Here we see the trade-off between validity and cost for our algorithm, labeled as alg1, and also for ROAR. For our method, we present results across various lambda values, while for ROAR, lambda is fixed at 0.1, since varying it further doesn't significantly impact its outcomes. The plot on the left shows the trade-off for logistic regression, while the plot on the right shows the results for a three-layer deep neural network. Although ROAR achieves a relatively lower cost, its recourse validity is substantially lower than of our algorithm. To address the second challenge of the high price of recourse, we adopt the Learning-Augmented framework, also known as learning with predictions. The aim here is to perform nearly optimally when the predictions are accurate, while still maintaining robust worst-case guarantees if the predictions turn out to be unreliable. Learning-Augmented has been applied to many domains like algorithms and data structures, mechanism design, privacy-preserving data analysis, and there is even a website called Algorithms with Predictions that tracks papers that use the Learning-Augmented framework. So returning to our example with Alice, suppose we do receive a prediction about how the bank's model might change, and this prediction could be highly inaccurate. How can we make use of it? So our algorithm takes into account two aspects: robustness, which reflects performance when the prediction is poor, and consistency, which reflects performance when the prediction is accurate. While optimizing for each separately is easy and straightforward, balancing both simultaneously is much more challenging. And we investigate algorithms that explore this trade-off between robustness and consistency, where beta acts as a tunable parameter to control this balance. Now, our algorithm is a greedy algorithm, similar to our robust approach, and it finds a solution in this setting. Here, we present the trade-offs between robustness and consistency for two scenarios. The plot on the left shows results using synthetic data, while on the right, it uses the German credit dataset. In both plots, each colored line represents the trade-off curve obtained from a different prediction, with each point along the curve corresponding to a specific beta value. At one extreme of the curve, where consistency is 0, robustness reaches its maximum value. At the other extreme, where robustness is 0, consistency is maximized. These curves illustrate how adjusting beta shifts the balance between robustness and consistency. So if we prioritize making our solution more robust, we have to give up some consistency and vice versa. If you would like to learn more about our contributions, here are the QR codes for our paper and our GitHub. Thank you.